All right, we are back, and I am back from my meeting. So excited to record some differential equations lectures that I'm still wearing my biking outfit. That's how awesome phase portraits are. So if you remember, let's go back to chapter 1, a little trip down memory lane. If we had an autonomous differential equation, a lot of times we would draw a phase line, right? And on this phase line, we would have equilibrium points. We would show the direction that the solutions moved. We could have sources. We could have sinks, otherwise known as unstable and stable nodes. And notice that when we did, push things down to one dimension, we kind of lose any sense of speed, right? Like we don't really see time here. We see the direction that y moves, depending on where y is. But again, we don't know how fast things are. Is it moving faster here or here? Is it moving faster here or here? We don't really have that information. And that was a phase line. It was really great for first order differential equations. And now we have something new. So we're gonna show a solution from our last equation. Remember, I said that we could solve this with Euler's method for, again, an adapted Euler's method for systems, which is covered in section 2.5. We could find approximations for these solutions. We could graph these solutions. It's helpful if we graph them together. There's another way of graphing them, though. Instead of graphing t versus the function value, we can graph what's the relationship between the rabbits and the foxes directly. And when we do that, we get a phase portrait. Okay, so let's notice a few things about this phase portrait. Okay, so first off, right, we are in the RF plane here. This shows the relationship of rabbits and foxes. There is no time here. Okay, just like when you're watching a differential equations lecture, time ceases to exist. You're just existing in a state of awe and wonder and October pressing buttons. Okay, so I actually have no idea. Oh yeah, she skipped ahead. She's excited to go to the next page too. All right, so we're in the RF plane. And let's say that we have some initial condition. Here our initial condition is P, which is maybe 1 unit of rabbits and half a unit of foxes. Again, maybe this is hundreds of rabbits. Maybe this is thousands of rabbits. Like who knows, right? And if we start here, this is telling us that time t equals 0. We start here and then follow this arrow. The rabbits are going to grow and the foxes are going to grow. Oh, and then the rabbits start declining, but the foxes are still growing. And then the foxes start declining. And eventually there's few enough foxes that the rabbits start to grow. And we're back where we started. And again, you can see that same information. That same information that we were talking about with these red points, right? In a different format. Again, reading graphs is so hard and so important in this class. So this is exactly what's happening right here. This is kind of similar to a phase line and kind of similar to how we would sketch our solutions. And again, a big call out here is that we don't really see, this is the only thing that tells us anything about time, is okay, we are moving along this curve. All right, and of course so that's pretty much what we have. Here is like one thing on in the phase portrait. A lot of times in our phase portrait, we're going to show many solutions, and so we could go to the next page and see that. So here, right, I'm plotting many solutions. So these are many solutions for different initial conditions, just like when we were doing slope fields. And again, we would say, okay, maybe there's a solution here and a solution here, and maybe another solution here, right? All different solutions for different initial conditions. This is exactly what we have in our phase portrait. Okay, so the other one was like an unfinished phase portrait. So like this is kind of the start of one. Okay, but usually we draw a lot. I guess they're both phase portraits. This just has more information. Notice a special call out here, right? We have an equilibrium solution here. We have an equilibrium solution here. And those are the only two equilibrium solutions that we found earlier. It turns out they are the only equilibrium solutions. And then again, depending on our initial conditions, we could be circling that equilibrium solution pretty close or much farther away. Remember that we had other things as well, right? Other things in our analysis for these rabbits and foxes, right? We said if there were no rabbits, the foxes would decay over time. We could actually include this. I don't know why the book doesn't, but if there are no rabbits, if the rabbits are equal to 0, the foxes are decaying. So there's really also a blue line right here, right? This is also part. And similarly, if there's no foxes, we said the rabbits are growing. All right. And I think the book actually didn't include them because if F is 0 or if R is 0, it's not very interesting. But they did include the equilibrium point. So anyway, these are two more blue curves that we could draw that have somewhat qualitatively different behavior than the other ones. Most curves here are going to oscillate for this model. All right. And yeah, a couple of conclusions that we can make. And again, this is useful sometimes, this phase portrait. This is useful sometimes, right? Plotting each function individually over time. This gives us a lot more information about time. This shows us, the very specific relationship in one way. It shows us that these are periodic, and this shows us different interactions, right? We can see the equilibrium solutions here, whereas we could not see the equilibrium solutions, I believe, in the other model, graph. And then again, can also see that they're periodic, right? They're periodic because if you start here, you will go all the way around, pretend I can follow the lines, and you're going to get back to where you started, and you'll keep on going around and around and around. So both things show periodicity and such stuff like that. All right, I think that's pretty much it. That's a phase portrait. Again, this book is pretty casual, not that formal about introducing a lot of these things. So we're not going to give technical definitions for these sorts of things. But the phase portrait is essentially, okay, go into the plane that has your two functions. So here we're looking at the RF plane and plot the solutions, like plot various solutions. Again, you're not going to be doing this by hand. You're going to be using numerical techniques to approximate these. But realistically, mostly you're going to be reading them, not making them yourselves. And then so interpreting them is going to be interesting. And yeah, we can see what direction they're moving based on how the functions are behaving. And that's pretty much it for phase portraits. A good second way of visualizing solutions to systems of ordinary differential equations.